Alright, here's a little bit of background on quantum numbers, and it will be a great introduction before we start talking about electron configuration. So let's start with the Heisenberg uncertainty principle, which is essentially why we do electron configuration. So the Heisenberg uncertainty principle tells us that we cannot know the speed and the position of an electron at the same time, and we know that because nothing in nature is ever stagnant, and so electrons are always moving, and if electrons are always moving, we can't actually pinpoint the exact place that they are. But we can, using electron configuration, and we'll get to that in just a second in the slides, we can predict where the most likely place it is going to be around the nucleus. And when I say it, I mean an electron. So we'll talk a lot about electron density. So electron density is the distribution surrounding the nucleus in a hydrogen atom, and there's a higher probability of finding an electron closer to the nucleus. And we'll get into why in the periodic trends unit, which is the next unit coming up. Quantum numbers are how we describe the pattern of behavior for electrons and how we describe the region where electrons can most likely be found, or electron density. So we'll use 4 quantum numbers to help us figure out the behavior and where most likely those electrons are going to be around the nucleus. Again, we can't pinpoint the exact place, but we can predict where they're going to be based on those quantum numbers. So quantum numbers, the chemist's way of describing an orbital and predicting where an electron should be, has a 4-character address, and we'll call all 4 of these our quantum numbers, and we'll define them further in just a minute. N, L, M, and spin, and it's like talking about an address. So it's like talking about N is our city, L is our street, M is the maybe apartment building, and spin is the apartment number. So maybe we're living in the same apartment building, and this is maybe saying this is apartment A, and another spin could be apartment B. I'll build on that when we talk further about some more rules in this unit. So again, there's 4 quantum numbers, N, L, M, and spin. So our first quantum number is just the principal energy level, or shell. So it's the average distance from the nucleus. The larger the N value, the further away from the nucleus that the electron is most likely to be. And so if you notice, there are possible 1 through 7 shells, and also if you look at the periodic table, there are 7 rows. So those correspond, the principal quantum number corresponds with the row on the periodic table. And we'll dive into this further when you watch the electron configuration introduction video. So the total number of orbitals in a shell is n squared, and we'll talk about sublevels to follow, and we'll actually follow up on this one in a minute just to show you how many electrons can be in each orbital. That's why we talk about that. The next quantum number is angular momentum, and so this is just the shape of the orbital. So the possible number of subshells is in each orbital is letter n, and our angular momentum is denoted with an L. So our shapes available are S, P, D, and F. S is a circle, P is a dumbbell shape, D is like a complex dumbbell or flower, F is too complex to explain what it looks like. But what we can do is predict, especially using these quantum numbers and these shapes of these orbitals, what we'll call them as an orbital, where the electron is most likely to be found around the nucleus. So if I have an electron in an s orbital, I can predict that it's going to be most likely in a spherical shape around the nucleus. If I have an electron residing in the p orbital, I can predict that it's going to be in the dumbbell shape around the nucleus. So hopefully that kind of helps with understanding what we mean about electron density and where we can predict those electrons to be around the nucleus. Our next quantum number is the orientation of the shape around the nucleus, and this is like a 3-dimensional axis of a graph. So we'll get into why we have to talk about these 3 dimensions, but we just need to know that they exist. When we write electron configuration, we're not really going to dive into splitting up into the different 3 dimensions, but we need to know that my p orbital, for example, will exist on the x, z, and y axis. And so hopefully you can kind of see we have 3 different possible shapes of our p orbital, or orientations of our p orbital. That will come in handy in just a moment. So the s orbital here as you can see, only has one shape, so it doesn't need to necessarily exist on the three different axes. Pardon me, I'll go back here. The p orbital has three different shapes, so it's existing on the x, y, and z axis. And the d orbital is also existing on the x, y, and z axis, but as you can see, there's also some varying shapes, especially this one. And so we'll get into this further later again, but electrons are going to occupy these orbitals, and this is again how we can predict where electrons are most likely going to be around the nucleus. So S has one shape, P has three possible shapes, D has 5 possible shapes, and F actually has 7 possible shapes. Here's our F, and that's quite a few possible shapes here, and again, as you can see, this is why it's too complex to explain exactly what the F orbital looks like. Here's just an electron density picture of those orbitals, the SPD, in a little bit more detail and in a real-life picture. Our last quantum number is spin, and so spin just tells us whether or not the electron is spinning at a plus half or a minus half. I like to think about it like this, as an up arrow or a down arrow, and so I like to think about it when we put shoes in a shoebox, we need to have one go up and the other go down so that both can fit in the box together. So in order for an electron to fit in an orbital, one has to spin up and the other has to spin down. And we'll follow up with this when we talk about orbital diagrams later. A single orbital can hold a maximum of 2 electrons, but they must have opposite spins. So just kind of how you fit 2 shoes in a shoebox, they must have opposite spins. So here's our review of quantum numbers. We've got energy level, shape, axis, and spin. We'll talk about energy level and shape mainly when we talk about electron configuration. You'll learn about energy levels when we talk about Bohr models, and then when we talk about orbital diagrams, we'll apply the up or down spin. So each shape for our orbitals can only hold 2 electrons. So the 1 has 1 s, so it can only hold 2 electrons total. The p has 3 different shapes, so it can hold 6 total electrons, and the d has 5 different shapes, so it can hold 10 total electrons in the d orbital. The f has 7 different shapes, so it can hold 14 electrons. So when we talk about orbitals, the maximum number of electrons that can be placed in each subshell is determined by the number of orbitals. So the subshell, again, remember, is s, p, d, or f. So our orbital for our s, we only have 1. So I want you to draw in the arrows, and we'll revisit this slide when we talk about orbital diagrams, but I want you to draw an up and a down arrow, like our shoebox. The maximum number of electrons that will fit in this is 2. So the p has 3 shapes, and I want you to draw the arrows like that. So our maximum number of electrons that can fit in the p subshell is 6. D has 5 shapes, so the maximum number is 10, and F has 7 shapes, and the maximum number is 14. So 7 shapes in each subshell for F. D has 5 shapes, P has 3, S has 1. I think this will continue to make sense when we talk about electron configuration. So if it's a little bit confusing now, that's okay. Again, this is just an introduction slide. We'll talk more about electron configuration, and then we're going to follow up in class with even more discussion about all of this. So again, this is just introduction. Quantum numbers, so our possible combinations here. This slide is just talking about how many electrons per energy level that we can have. So let's talk about it. So our energy level number 1 has 1 subshell, and it's the s subshell. And in the s subshell, we only have 1 orbital. That means that, calculation-wise, because the number of orbitals is n squared, we talked about that in some of the first slides. So 1 squared equals 1. So I have 1 orbital. So electrons per main energy level, I can calculate that 2n squared. So 2 times 1 squared is 2. So this is basically a mathematical breakdown of the slide that we just looked at. In level 2, we have 2 possible subshells, s and p. That means that in the s I have 1 orbital, and in the p I have 3. So I have a total of 4 orbitals, which means I can have a total of 8 electrons per energy in that second energy level. The third energy level, or the third quantum number n, third level on the periodic table, the third row, lots of different ways to say it, has s, p, and d, which means that I have a total of 9 possible orbitals. That means that in the third energy level I can have a total of 18 possible electrons. So hopefully you're thinking to yourself, in physical science you learned that our outer electron shells can only hold 8 total electrons. And that's correct, and we'll follow up in class in terms of where those other 10 electrons go when we're writing electron configuration and when we're talking about that further in class. So then level 4 has all 4 subshells in it, which means it has a total of 16 orbitals, which means it can hold a total of 32 electrons. Again, same reasoning as level 3. We'll talk more about why that can have more than 8 electrons. There's still only going to be 8 in the outer shell, so we'll talk about where the rest of those go. Okay, please watch the electron configuration introduction video and come ready to class to work on electron configuration together.